Hello, science students. Today we're going to talk about electric force. So up to this point, we have talked about forces long back in the physics unit, and more recently we've been talking about waves. Now we're going to kind of shrink things down to more of the particle scale and start talking about electric forces and where those come from. So our goal by the end of this video is for you to be able to describe the direction of the electric force on charged objects. We're not going to talk about the total force necessarily so much as which way will things be pushed. So a definition of an electric force is an attractive or repulsive force, so a push or a pull, between two objects that each have a net charge. So each object must be charged. If one of them is neutral or has no charge, then we would not see an electric force. So two key pieces, it's going to be attractive or repulsive, and it's got to be between two charged objects. Let's take a look at some examples. So the first thing we know, and you've probably heard this before, is that like charges repel. So two types of charges, positive and negative. So if we have two positive charges, as an example, the direction of the force on those charges would be directly away from each other. Okay, or the other version is also true. So if I have two negative charges, so they each have a negative charge, they would also experience a force in opposite directions. Now, our rule that for every action there's an equal and opposite reaction, Newton's third law, still applies to charges. So even if one of the charges was much bigger than the other, the total force would be the same. The acceleration might be different if they have different masses, but the forces would be the same. And that's what these arrows represent here. Okay, opposite charges attract. So if I have a positive and a negative charge, instead of the forces being away from each other, they would be towards each other. Okay, and the reverse would still be true. If it's a negative and then a positive, the forces would still be towards each other. Okay, so one more time, just as a reminder, these force arrows, their length represents their magnitude or how large the force is, and then the direction obviously represents the direction or which way that force is moving. Okay, let's take a quick look at Coulomb's law. So Coulomb's law is how we would normally calculate the force between two charges. We're not going to have you do that here because the numbers are usually very big and very small. So let's talk about it briefly. So Coulomb's law is the force is equal to Coulomb's constant, which is just a number. I'm not going to worry about what it is today. Multiplied by charge at number 1, or Q1, and Q2, which would be the charge number 2. That's how much charge they have. So how much charge in something called coulombs. Again, we're not as worried about units here, but the Coulomb's law, they named the unit for charge after the same scientist. So, and then finally, R is the distance between the charges. So here's the relationship you need to know. More charge equals more force. And this is kind of a linear relationship. So, for example, if a charge is doubled, the force will also be doubled. So this should kind of make sense. So kind of like, this is very similar to the gravitational force equation. So if we have twice as much mass, we have twice as much force. In this case, if we have twice as much charge, we'd have twice as much force. If we had 3 times as much charge, we'd have 3 times as much force. Now, if we doubled each of them, it's a little bit different. We're not going to worry about that so much today. Okay, greater distance, and that's what R represents. So R is the distance between the charges. The bigger that is, the smaller the force. That's why it's the bottom of the fraction, and it's squared. So greater distance equals less force. So just like when there's more distance between masses, if there's more distance between charges, they affect each other less, and therefore the force is not as large. So just as an example, so if R is doubled, or the distance is doubled, since it's squared, the force will be 1/4 as great. So if we tripled it, it'd be 1/9. If we quadrupled it, it'd be 1/16. Because this is squared, every time we change R, the effect of that is also squared. So since I cut it in half, or I doubled it, and it's an inverse relationship, it's going to be 1/4. If I tripled it, it'd be 1/9. Okay, not as big a deal, but I want you to get an idea of how these charges interact. So if you've ever tried to push two magnets together, it's not exactly the same force, but if you push them together, you can really feel as you get closer and closer, it gets much, much stronger. Okay, same thing with charges. If you push together two positive charges or two negative charges, the force gets much, much stronger. So what did we learn today? We learned the relationship between force, Coulomb's constant, charges, and distance. We talked a little bit about like charges repel or push each other apart, opposite charges attract or pull each other together. And we kind of learned that that electric force is what we saw there, an attractive or repulsive force between two objects that each have a net charge. Okay, thanks for watching.